Today's class is in continuation to the last class. In the last class, I have discussed about Ampere circuit law and its applications. There are three applications. In the last class, I have discussed the first two applications. In today's class, I will explain clearly about the infinitely long coaxial transmission line. What are those first two applications? In the first two applications, we have found the magnetic field intensity due to flow of current in the infinitely long conductor. Okay. In the same way, we have found magnetic field intensity for infinitely long sheet of current. And today, in infinitely long coaxial transmission line, there will be two concentric cylindrical conductors. Okay, I will show you the cross-sectional area of those two cylindrical conductors. These are the two conductors. This is inner one and this is outer one. The inner one has the radius A. Inner one has radius A shown by this white color line. Radius is A and the outer conductor is shown by different color. This is outer conductor and thickness is T. And radius of this outer conductor is B and the thickness is T. So radius of this outer line, the circular line is B plus T. Okay. And this dashed line is nothing but Amperian path L1, L2, L3 and L4. So there are four different cases. We will consider one by one and then explain how to find out the magnetic field intensity due to Amperian path L1, Amperian path L2, Amperian path L3 and Amperian path L4. Okay. First case. First I will write the all four cases. The radius of this Amperian path is rho. Okay. Case 1. Case 1. 0 is less than rho is less than A. That is the inner conductor. Okay, inner cylindrical conductor whose radius is A, and this Amperian path, this is the Amperian path shown by dotted line. It lies between 0 and A. And case 2, that is L2. L2 is lying between conductor 1 and conductor 2. That is inner conductor and outer conductor. That is A is less than rho is less than B. And case 3, that is the Amperian path is lying in the outer conductor, outer cylindrical conductor, that is L3. That case 3 is B is less than rho less than B plus T. And last case 4 is rho is greater than B plus T. Okay, we will consider each case one by one and then find out magnetic field intensity due to flow of currents. Two currents are there. One current is moving away from the board in the inner conductor, and this is outer conductor. Inner conductor, this is dot, circle dot is so the direction of current. Current will be flowing like this. And here the outer conductor is into the board, shown by this into circled into. Okay, that is flow into the board. So the unit vector for this inner conductor for the current is A z cap, and for this it is minus A z cap. For the outer conductor, current is flowing into the board. So for current density for inner conductor, it is A z cap, direction of current density in inner conductor, and direction of current density in outer conductor is minus A z cap. Okay, I will consider the case 1 now. Case 1, this Ampere circuit law is integral H dot dl is equal to current enclosed by the Amperian path, and differential dl is differential length of the Amperian path, and H is the magnetic field intensity tangential to the Amperian path, that is the direction of A phi. Since we are using the cylindrical conductor, coordinates. So current enclosed is equal to integral J dot ds. J is the current density and ds is the differential surface. So First we will do this integral H dot dl. I will draw for inner conductor diagram separately. This is the inner conductor. Let this be inner conductor. And the current is moving like this, and radius is A, and this is the Amperean path. This is Amperean path whose radius is rho. Whose radius is rho. Whose radius is rho. Okay, and the direction of this magnetic field intensity H is the direction of A phi cap. A phi cap. And dl is what? dl is nothing, differential length of this Amperean path. Okay, so H is what? H is H into A phi cap dot dl. What is dl in cylindrical coordinates? dl is equal to d rho into A rho cap plus rho into d phi into A phi cap plus dz into Az cap. Okay, we substitute here. So integral H A phi cap dot dl is d rho A rho cap plus rho into d phi into A phi cap plus dz into Az cap, which is equal to integral, I take out this h since it is constant, A phi cap. So A phi cap, not A, d rho into A rho cap. So A phi cap dot A rho cap. So A phi cap is the dot product of A rho cap, dot product of A phi cap, and dot product of Az cap. So H is taken out since it is a constant. A phi cap dot A rho cap is 0. Since angle between these two vectors is unit vectors is 90 degrees, so it is 0. Cos 90 is 0. Okay, and plus A phi cap, dot product of A phi cap is 1. So we can write rho into d phi, rho into d phi, that A phi cap dot A phi cap is 1. Dot product of two unit vectors is 1 plus A phi cap dot A z cap is 0 since angle is 90 degrees. So finally we will get H dot TL is equal to H integral rho d phi from 0 to 2 pi, which is equal to H rho integral 0 to 2 pi d phi, which is equal to H rho into phi 0 to 2 pi, which is equal to H into 2 pi rho. H into 2 pi rho. Okay, this is same for all the Amperean paths. So I will not derive again this expression. Integral H dot dl is equal to H into 2 pi rho for L1, L2, L3 and L4. For all the cases, H into 2 pi rho. Only rho value differs. Okay, so this is equal to the H dot dl integral H dot dl is equal to H into 2 pi rho. H into 2 pi rho. H into 2 pi rho. Now let us find out J dot ds now. J dot ds. What is J? Look at the board. The current will be flowing in this direction. And what is the area of cross section? Area of cross section is pi a square. This area, total area of this circle is pi into a square. So current divided by area of cross section gives the current density. That is J is equal to I by phi into a square. That is the complete, we will consider the complete cross-sectional area to find out the current density. So J is equal to I by pi a square, and direction is a z cap, since it is flowing like this. And what about ds? ds is, this vector is which direction? In the direction of z axis. Okay, area will be, that is, that plane will be lying on the board, and its direction is normal, that is, its direction is the direction of the z axis. So what is ds now? We have to consider like this. From this, its vector is a z cap, the direction of a z cap, and we have to multiply these two. It is rho into d rho into d rho into d phi into a z. That is the different surface area. Okay, different surface area. If you consider small surface area, that ds is equal to rho into d rho into d phi a z cap. So you substitute here, then you find out the expression now. Integral, what is z? Z is I by pi into a square, integral, since it is a constant taken out, a z cap dot, what is ds? Rho into d rho into d phi a z cap. A z cap. So we have to multiply, we have to run the dot product of this a z cap is 1. So it is equal to I by phi a square integral rho d rho integral d phi. Integral d phi. Rho varies from, it is case 1. So rho varies from 0 to rho only. 0 to rho. Ambient path is, radius is rho. So till ambient path it is rho only, from 0 to rho, and angle is 360 degrees, 0 to 2 pi. After integrating, we will get I by pi a square rho by 2 rho square by 2 0 to rho and phi 0 to 2 pi, which is equal to I by pi a square rho square into 2 pi into 2 pi. Now let us equate these two now. There is integral h dot dl is this one, and integral j dot ds is this expression. Let us equate. So h into 2 pi rho is equal to rho square by pi a square. So this pi will get cancelled. Okay, and 2 is there, 2 also will get cancelled by 2, 2 also will get cancelled. So finally we will get rho square by a square, which is equal to rho square by a square, rho square by a square into y. So is equal to rho square by a square into y. So h is equal to rho square by, this rho will get cancelled, will get rho by 2 pi a square, 2 pi a square a phi cap with the direction amperes per meter, the units. So for the first case, we got this magnetic field intensity as rho by 2 pi a square into a phi cap amperes per meter. Okay, for case 1. Let us do for case 2 now. Case 2, that is L2. This is inner conductor whose radius is A, and the current is moving out like this, and this is the ambient path. This is ambient path, and whose radius is rho. Whose radius is rho. This is ambient path. Ambient path. and radius is rho. So integral h dot dl is equal to 2 pi h into 2 pi rho. Then what is I enclosed? Current enclosed by this Amperian path. Current enclosed by this Amperian path is what? I only. No need to derive anything. It is enclosing the complete current, not part of it. So it is equal to I. So H is equal to I by 2 pi rho. 2 pi rho, and direction is A by cap, amperes per meter. For second case, H is equal to I by 2 pi rho, A by cap, amperes per meter. Very easy. So second case is over. First is over. Let us consider the third case, okay, which is somewhat difficult. So be attentive. Third case, draw the diagram separately. Third case is L3. So inner conductor is there. Inner conductor is there, whose radius is A, and the current is moving out like this. Current is moving out like this. Okay, this inner conductor, and L3, where it is L3 in the outer conductor. Okay, so I'll draw the outer conductor. This is outer conductor. This is outer conductor. This is B, and this is thickness. This is thickness. So outer circle radius is B plus T. Okay, and the current is flowing into the board. The Amperian path is, it is in the outer cylindrical conductor. This is the Amperian path. This is Amperian path. So this radius is rho. This radius is rho. Radius is rho. This is Amperian path. For the outer conductor, current is entering into the board. For the inner conductor, current is moving out of the board. That is leaving the board like this. So this Ampere circuit law is H dot dl. H dot dl is equal to, dl is what? dl is the differential Ampere path, differential length of the Ampere path. So which is equal to, what is the current enclosed by this Ampere path? This is the Ampere path, Amperian path. Amperian path. It is enclosing inner conductor current completely, and it is enclosing part of the current in the current flowing through the outer conductor, outer cylindrical conductor. So this dashed line. So this current it is enclosing. Okay. So the Amperian path encloses I completely, and I dash is part of I which is entering into the board, and dot, this circle dot is leaving the board like this, is going like this, and I is current in the outer conductor is entering into the board. Now let us find out this. Now I is complete current. Let us find I dash. For I dash is equal to J dot ds. J dot ds, and I already told you integral H dot dl is equal to 2 pi into H into 2 pi rho. I will not do this derivation again for this. H into 2 pi rho, H dot dl, and let us find out the currents now. I is, need not find out any derivation is there for I. Let us find out I dash now, and then add these two I and I dash. I dash is equal to J dot ds. J and ds are both are vectors. What is J? J is equal to, what is current flowing through the outer cylindrical conductor, that is I. That is I is into the board. So minus I by what is the area of cross section? Area of cross section is the complete strip. So the area of outer circle minus area of this circle, this one. Okay, I am not saying inner because inner is related to this inner circle. Outer circle area minus inner circle area gives this cross sectional area. So I by pi into outer circle area is b plus t whole square, that is pi b plus t whole square minus pi b square minus b square. Okay, which gives the current density. It is into the board, so minus az cap, minus az cap. So j direction minus az cap, it is into the board, and current is minus as, since it is opposite to the flow of current in the inner cylindrical conductor. So this is equal to minus I minus az cap by, we open the brackets, 5 into t square plus 2bt. b square will get cancelled. So this is j, whose direction is minus az cap. And what about ds? Already we have given an expression, found an expression, that is rho into, that is rho into d rho into d phi. Okay, this is ds and minus az cap. Okay, this difference surface vector is into the board, so minus az cap. Let us find out this expression now. Integral j dot ds now. So I dash is equal to, what is j? What is j? J is minus I by 5 into t square plus 2b, t square plus 2b, 2b, 2bt, 2bt, t square plus 2bt. Okay, b square plus 2 square plus 2bt minus b square. Okay, we will get t square plus 2bt into integral minus az cap dot, what is ds? Rho into d rho into d phi into minus az cap. Okay, finally it is equal to, I dash equal to minus I by 5 into t square plus 2bt integral, this minus az cap dot minus az cap is equal to 1. Okay, so this is, I am writing here, rho d rho, integrating from 0 b to rho, because the ambient path is lying between b and b plus t, so it is up to ambient path. Ambient path radius is rho, so b to rho, rho d rho, and integral d phi from 0 to 2 pi. Let us integrate now. So which is equal to minus I by 5 into t square plus 2bt integral rho d rho is rho square by 2, rho square by 2, 0 to rho, no, b to rho, and phi is from 0 to 2 pi, so which is equal to minus I by 5 into t square plus 2bt t square plus 2bt, rho square is rho square minus b square after substituting these limits by 2 into 2 pi. Substitute 0 0 minus 2 pi minus 0. So this 2 and this 2 and this pi and this pi will get cancelled. So I dash is equal to minus I by, or you can write minus rho square minus b square by t square plus 2bt into I, into I. This is I dash. Now let us add these two now, I and I dash. that will be equal to this, that is H into 2 pi rho, and from that expression we'll find out the magnetic field intensity H. So this H into 2 pi rho is equal to I plus I. I am taking I common, I minus, it is 1 minus rho square minus b square by t square plus 2bt. 2bt, 2bt, what is the direction? 2bt. Now what is H now? H is equal to I by 2 pi rho I minus rho square minus b square, rho square minus b square by t square plus 2bt. So what are the units for H? Ampere per meter. And what is the direction of H? A phi cap. A phi cap. Ampere per meter. So for L3, H is equal to the magnetic field intensity is equal to this expression. For L3, this is the diagram corresponding to L3. And for L4, it will be 0. I will tell you how it is 0. So this third case also over. For L4 now, for L4, the L4, what is L4? L4 is the Amperean circuit, Amperean path. It is enclosing two currents, I, that is which is flowing into the board, I which is leaving the board. So both will cancel each other. So this H dot dl is equal to 0. I plus I, that is I minus I, which is equal to 0. I already derived this is H into 2 pi rho is equal to 0. So H is equal to 0 for L3. Okay. With this, the Ampere circuit law and its applications completed.